All right, we're going to start 9.4. Sorry about the echo. Okay, and what I want to start off with is, I think in this class I had accidentally done this. But you remember I told you about Euler, and that Euler had played around with numbers, and he added 1 plus 2 plus 3 up to 98, 99, and 100. And then what he did is he rearranged the numbers in a backwards fashion and added them together. So he added each column. And every time he added a column, they added up to 101 each time. Okay? So how many numbers of 101 did he have? 100. So you could actually quickly find the sum of 1 to 100. Now this was 2 sets of 1 to 100. And so we divided by 2. So if you think about this in general, he had n terms times one more than that divided by 2. So what we're going to move into the second part of this lesson is sums of powers of integers. So if I want to add 1 plus 2 plus 3 plus 4 up to n, I can immediately find, say, the sum of the first 40 by putting in 40 times 41 divided by 2. And that'll give me the sum of the first 40 numbers. Okay? Now, in number 2, if I have 1 squared plus 2 squared plus 3 squared up to n squared, there's a formula that will compute that for you. It's n times n plus 1 times 2n plus 1 over 6. Yeah, Chase?
Do you find notes a cheat sheet thing?
Yes.
Are we allowed to put these on there? Or
Absolutely. No, these are formulas. This is a formula set. Yeah, because see, it's going 1 squared plus 2 squared plus 3 squared up to n squared. So it's not a worked out example. Good question. All right, the same thing with the cubes. I'll tell you the first and the second one are the most common. And you'll find that you're going to accidentally memorize the first one, n times n plus 1 over 2. I mean, without even much effort. After you do enough problems, you're going to just know that one. So for the next quiz, you're allowed to bring an index card with these 5 on it. Okay? I'm not going to make you memorize these, but you do need to know how to work them. Okay, so then we're going to need to come back to these periodically as we do the next set of problems. Okay? So let's look at example 5. It says we want to find the sum where n runs from 1 to 7 of n cubed, which we know is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed. Well, what I want you to do is look at the formula. The formula says if I want to add up the sum of cubed terms, the formula is n squared times n plus 1 squared over 4. And n is how many, starting with 1 up to n. So what am I going to plug in for n here? 7. So this will be 7 squared times. Now what would I put in for n plus 1? 8. And you can definitely use your calculator here. So let's do 7 squared times 8 squared divided by 4. Okay, and I got 784. You guys getting the same thing? Awesome. All right, now let's look at letter B. We learned in an earlier section when we first learned about the sigma notation, this notation right here, sigma, that if you had a constant out front, you could pull the constant out. And if you had subtraction, we could separate the subtraction. And if you're going to take calculus, this is going to help you tremendously with some manipulation that happens in calculus. So the first thing I'm going to do is use the property of summation that says I can break that apart into this a difference of two sums. Then I'm going to do further manipulation by bringing the 6 out front. I'm sorry, I don't know what's wrong with my little wand.
Can we bring the 4 out too?
Yes, exactly. So I'm going to rewrite this as 6 times the sum, where n runs from 1 to 4 of n, minus 4 times the sum, n runs from 1 to 4 of n squared. Then you look up above in our formulas, and this will be 6 times the summation for n was n times n plus 1 over 2 minus 4 times, and then I'm looking at the formula for summation n squared, and that's n times n plus 1 times 2n plus 1 all over 6. But what is n here? 4. N is 4, you're right. So let's do a little bit of simplifying. 2 goes into 6 3 times. So that's 3 times 4 times 5. Where did I get the 5 from?
You
Add 1 to it, okay? All right, then let's handle the 4 and the 6. 2 goes into 4 twice. 2 goes into 6 3 times. So I'm going to have a 2 times 4 times 5. And what am I going to put in for 2n plus 1? 9. Good. So this is 60. Now 3 goes into 9 3 times. And then I got 120. So that is negative 60. Sorry, I ran into letter D there. I'll have to erase it in a moment. All right, questions on letter B? All right, let's look at letter C then. So I can make this the sum where n runs from 1 to 5, and we're going to break this apart into n squared plus the sum that runs from 1 to 5 of n. Okay? So we use the formula for the sum of n squared. That's n times n plus 1 times 2n plus 1 over 6. Thank you. Plus, the sum of n terms is n times n plus 1 over 2. Then you're going to substitute that n is 5. All right, so I'll give you a head start. Plug in that n is 5, and let's see if we get the same answer. So what I've done is I've just plugged in what I know. Do some simplifying. The 6's cancel, so I have 5 times 11 is 55. 2 goes into 6 3 times, so I have 15. 55 plus 15 is 70. All right, try letter D on your own. Summation. K runs from 1 to 8 of 3k. So use the properties for summation to pull out the 3. Did you guys get 108? Okay. Now, why did I use the letter K in this one instead of an N?
Oh, yeah, but it's weird.
Yeah, the other problems had N as the variable in the expression. I'm not going to take any points off on a quiz or a test if you use the N, but I just wanted you to notice that. Okay, so let's flip the page. All right, it says finding a formula for the nth term of a sequence. So do you remember in 9.1, some of us struggled with, okay, I don't know, I don't see them. I don't see the n factorial. I don't see n plus 2. We didn't see that. So we're going to get a nice strategy in this lesson to help us out. It says, to find a formula for the nth term of a sequence, consider these guidelines. Number 1, calculate the first several terms of the sequence. It is often a good idea to write the terms in both simplified and factored forms. Step 2, try to find a recognizable pattern for the terms and write a formula for the nth term of the sequence. This is your hypothesis or conjecture. You might try computing 1 or 2 more terms in the sequence to test your hypothesis. So if you look at example 6, here's what I like to do. I like to make a chart for n and then what would be the nth term. Because then I can see oftentimes a relationship between the n and the term value. So if I want to find the nth term, it's like I'm going out all the way to n. So what could we do to n to get the nth term? This one's kind of easy. Yeah, all you're doing is you're taking its 10 times n. So your nth term is 10 times n. Okay, that was fairly clear. Now in this one, if I do that same idea, and we talked about this strategy in 9.1, okay, clearly we're not multiplying by the same number to each term. But I notice a common difference. What is the common difference between each pair of numbers in the sequence? 3. Okay, so what that does for me, when I know the common difference, I can do 3n, and then n is the term number. So if I take 3 times 1, what do I have to do to 3 times 1 to produce a 4? Plus 1. Well, let's test it, though, to make sure. 2 times 3 is 6, plus 1 is 7. That works. 3 times 3 is 9, plus 1 is 10. 4 times 3 is 12, plus 1 is 13. 5 times 3 is 15, plus 1. So the nth term you find by 3n plus 1. Okay? Now, let's look at example 8. It says, find the nth term in the sequence. So let's make our chart. The first term is 2. The second term, -3. The third term is -8. And so on. So there is a common difference here, right? But it's going down by 5. So if it's going down by 5, that's -5n. Okay, that's -5n. And then what would I need to do to -5n to figure out, say, the first term? You would have to add 7. That's right. Okay? And if you do notice it's arithmetic, we can use our DNA. Okay, let me write that down. If we know it's arithmetic, you can use DNA. That was our little reminder that it was this formula.
Why did we add 7
if you know the first term is 1, okay, or n is 1, if I take negative 5 times 1, that's negative 5. What do I need to add to get to this term? I would have to add 7. And we check it. 2 times negative 5 is negative 10, plus 7 gives me negative 3. Okay? So there's your nth term. Okay, how about in number 9? It says, my first term is 3. My second term is 5. My third term is 8. The fourth term is 12. The fifth term is 17. The sixth term is 23. Okay? Okay. So now, in this one, if I look at the differences, whoops, sorry, I wrote something wrong there, hold on. That's actually a 4. There's a pattern with the differences, but they're not the same, right? So when this happens, we call this a first difference. A first difference, and when we did it up here, in example 7 and example 8, the first difference produced a linear equation, an n to the first power. Well, what you can do with this same pattern idea is you can take the first differences and take their differences, and if they have a common difference, this is actually quadratic. So a sub n is going to look like a n squared plus bn plus c. Okay? If you get to a second difference, it means it's quadratic. And we know the general quadratic equation. We're just using n instead of x. Well, how do you solve a quadratic equation? We don't know a, b, or c. So what I'm going to do is every ordered pair is n, comma, a sub n. Or it might be easier to think of it in terms of it's x, comma, y. So all you need is 3 equations to solve for 3 unknowns. So what I'm going to do is, let me change color so you can see the change I'm doing. I'm going to pick 1, comma, 3. So I would write 3 equals a times 1 squared plus b times 1 plus c. And if I tidy that up, that would be 3 equals 1a plus 1b plus 1c. I'm going to pick a second ordered pair, 2, comma, 5. And I would get 5 equals a times 2 squared plus b times 2 plus c. So all I'm doing is every ordered pair is n, comma, a sub n. And I'm plugging it into a sub n equals an squared plus bn plus c. So if I tidy this one up, I get 5 equals 4a plus 2b plus 1c. In a moment, you're going to see why I'm really emphasizing the 1 in front of this a, b, and c. All right, and we need 3 equations to solve for 3 unknowns. So I take the third point. 8 equals a times 3 squared plus b times 3 plus c. So I can tidy that up and I get 8 equals 9a plus 3b plus 1c. Now what I'm going to do is I'm going to solve this system on my calculator using an inverse matrix. So in matrix A, we're going to put 1, 1, 1, 4, 2, 1, 9, 3, 1. This will be matrix A. So it's a 3 by 3 matrix. In matrix B, you put 3, 5, 8. It's a 3 by 1 matrix. You're supposed to remember how to do matrices on your calculator. We did them in Algebra 2. We've seen them earlier this year. And then does anybody remember, once you get matrix A in and matrix B in, what are the keystrokes to solve the system?
Matrix A inverse matrix B.
Awesome, awesome. It's A inverse times B. Okay, you take A inverse times B. So what I'm getting is 1/2, 1/2, and 2. Are you guys getting it yet?
How do you make the matrix inverse again?
There's a button. It's the same button as the matrix button. You just press that button.
Yeah, you just pull up your matrix A under name and hit the X inverse key. Okay, so now what this means, these are the A, the B, and the C that were unknown in the system. So A sub n is 1/2 n squared plus 1/2 B, or I'm sorry, n, plus 2. Pull up matrix A, and then you just press your X inverse key. You see the inverse button? X to the -1 is your inverse key. Times then matrix B. All right, we'll do another one of these, but I do want to do example 10, and then we'll come back with whatever time to do one more like example 9, because that's a little tricky, okay? So in example 10, it says find the nth term of the sequence. Well, the numerator, you can tell looks like some kind of power of 3, but I need it to be 3 to the 0 power first. So I'm going to make that numerator 3 to the n minus 1, because if n starts at 1, do you see how we get 3 to the 0? And then in the bottom, isn't that 5 to that same power? Because I really want 5 to the 0 first. So another way to write that, and maybe you already saw it that way, is couldn't we write it as 3/5 to the n minus 1 power as a fraction? Okay. All right, let's look at example 11. It's similar to example 9. In the textbook, they may write it this way, but I want you to understand that a sub 0 equals 3 is an ordered pair. That when n is 0, a sub n is 3. This is 1, 3, and this one's 4, 15. And something I should have stated is it does say in your textbook that sometimes it's quadratic. It'll say it is quadratic. That'll be a given. So if you know it's quadratic, you're going to have a sub n equals a n squared plus b times n plus c. So we're going to go through the process again. So if I plug in 0, 3, this is 3 equals a times 0 squared plus b times 0 plus c. What I would suggest you do, which I did on example 9, do your initial plug-in, but then beside it, create your system that you're going to use. It's a little bit clearer to deal with. So let me change color. So this would be 0a plus 0b plus 1c. Why am I putting, even though the a disappears, why am I putting the 0a, 0b, 1c? Why would I be doing that?
You have to plug it into the matrix.
You have to plug it into your matrix in the calculator, so we might as well be really clear about it. Okay, the next point is 1, 3. So this is 3 equals a times 1 squared plus b times 1 plus c. So all I'm doing here on the left of the screen is I'm plugging in that n is 1 and a sub n is 3. If it bothers you, like it's confusing to do n and a sub n, think of it as x and y, and that works. So I would get 3 equals 1a plus 1b plus 1c. Third point, 4 comma 15. 15 equals a times 4 squared plus b times 4 plus c. So I get 15 equals 16a plus 4b plus 1c. So my matrix A would be 0, 0, 1, 1, 1, 1, 16, 4, 1. I can already hear the buttons going. Matrix B is 3, 3, 15. And you type in your calculators A inverse times B. So you should be getting a solution in a moment. 1, -1, and 3. So that makes it a sub n equals n squared minus n plus 3. Okay, the 3 letters you're solving for are the lowercase a, b, c in this general equation. That's where you're plugging it into, okay? So again, I got A was 1, B is -1, and C is 3.